Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
The universe is expanding, and that physical spatial stretching is governed by a precise mathematical value known as the Hubble constant.
Right. It represents the exact rate of that current expansion.
Every single second, the very fabric of space between galaxies is stretching out in all directions. We are investigating what is undoubtedly the most critical unresolved paradox in modern astrophysics, the Hubble tension.
Yes. And we have to be clear, this is not a mere anomaly.
No, it is not a rounding error in the data. We are looking at a profound, fundamental discrepancy that threatens the axiomatic foundations of cosmology.
It truly is the absolute foundational metric. When we discuss cosmic expansion, you have to separate it from the idea of objects moving through pre-existing space. We are not talking about galaxies simply flying apart through empty space like shrapnel from a localized explosion.
General relativity dictates that spacetime itself is a malleable fabric. We are talking about the continuous, ongoing creation of new physical space between those objects.
Exactly. And the Hubble constant quantifies the exact current rate at which that fabric is stretching out. But the crisis, the Hubble tension, arises from a staggering dichotomy between two distinct sets of precision measurements.
Let us establish those two measurements. When astrophysicists analyze observations originating from the early universe, specifically the cosmic microwave background, the oldest light we can detect, emitted just hundreds of thousands of years after the Big Bang, they calculate one highly specific rate.
Usually that sits around 67 kilometers per second per megaparsec.
Right. However, when they use entirely different methodologies to measure the local, more recent observable universe, they arrive at a completely different rate.
Hovering around 73 kilometers per second per megaparsec.
And the margin of error on these two measurements has shrunk to the point where they no longer overlap. They are mathematically incompatible.
Which is the core of the problem. Both of these measurement methodologies rely on the identical fundamental laws of physics. The underlying math governing gravity, thermodynamics, and electromagnetism is exactly the same for both.
Therefore, the results should theoretically align perfectly.
They should. The fact that they don't points directly to an axiomatic conflict. We have two pristine rulers to measure the cosmos, built on the same physical laws, giving us entirely different dimensions.
Which forces the discipline to confront a highly uncomfortable objective scientific reality. Because our methodologies are logically sound, heavily cross-checked, and based on the same established physical laws, the lack of alignment dictates that we cannot simply tweak our existing models.
I mean, the standard model of cosmology, known as lambda CDM, is coming up short. The discrepancy implies a massive deficit, a literal gap in our current astrophysical framework.
We are facing a fundamental crisis. Resolving it requires entirely novel diagnostic tools. Because if our baseline understanding of how the universe expands is flawed, then our calculations regarding the age of the universe, its total geometric size, and its ultimate cosmological fate are all built on incredibly shaky ground.
Establishing a unified Hubble constant is an absolute imperative for comprehending the foundational mechanics of the cosmos.
So, if the established standard model is broken or incomplete, theoretical physicists must hypothesize what exactly we are missing in the dark sectors of the universe. There are three major variables currently debated to explain this deficit.
If you look at the cosmological models trying to patch this hole, the first major variable is early dark energy.
Now, dark energy is the dominant component of the universe today. It drives the accelerated expansion we currently observe. But this hypothesis introduces a completely different dynamic.
It proposes a temporary but highly influential cosmological influence that was active only during the universe's earliest epochs. The theoretical framework suggests that long before the current era of dark energy dominance, there was an additional distinct phase.
A scalar field of early dark energy that emerged and significantly altered the expansion rate when the universe was incredibly young.
Roughly 100,000 years after the Big Bang. This early dark energy would have acted as a massive temporary repelling force, boosting the expansion rate and fundamentally changing the size of the sound horizon.
The maximum distance acoustic waves could travel in the primordial plasma.
Precisely. And then, just as quickly as it appeared, it essentially decayed or faded away. If our current lambda-CDM models do not account for that early temporary boost, then our calculations for the Hubble constant derived from the cosmic microwave background will be fundamentally skewed when extrapolated to the present day.
Which means the early universe data isn't intrinsically wrong. Our mathematical bridge to the present is just missing a massive structural component.
Right. And that brings us to the second theoretical variable, dark matter and neutrino interactions.
To frame this accurately, you have to consider the inventory of the universe. Dark matter constitutes the vast majority of all mass. We cannot observe it electromagnetically, but its immense gravitational pull is what holds galaxies together.
While neutrinos, on the other hand, are the most abundant particles in the universe that actually possess mass, but they are incredibly elusive.
They are often categorized as ghostly particles because their cross-section for interaction is infinitesimally small. Trillions of them pass through your body every second without interacting with a single atom.
Under the standard model, we assume dark matter is entirely collisionless, and that neutrinos basically interact with nothing except via the weak nuclear force. But this hypothesis challenges that assumption directly.
It questions whether there are complex, unmapped theoretical interactions occurring between the massive invisible web of dark matter and a background sea of cosmic neutrinos.
If dark matter particles and neutrinos scatter off each other, even minutely, it would suppress the growth of cosmic structures in the early universe.
Right, because if these two immensely abundant components of the cosmos are interacting in ways particle physics has not yet quantified, those hidden physics would alter the density perturbations of the early universe.
That would completely distort our mathematical understanding of cosmic expansion. We would essentially be trying to balance an equation while completely ignoring a major mechanism by which the universe's ingredients behave and evolve.
And if those two variables weren't sufficiently complex, there is a third major hypothesis: the temporal evolution of dark energy.
Currently, the standard model treats dark energy as a cosmological constant. It is assumed to be a static, unchanging vacuum energy pushing space apart at a steady, exponential rate.
But what if it isn't static?
That is perhaps the most profound possibility currently under analysis. We are looking at the hypothesis that dark energy is not a constant force, but rather a highly dynamic, evolving phenomenon.
Theoretical physicists refer to this via the equation of state parameter.
Yes. If that parameter changes over time, it dictates that the actual density and repulsive pressure of dark energy shifts, grows, or weakens over vast cosmic timescales.
If dark energy is dynamic, its influence on universal expansion is entirely temporal.
Exactly. Comparing the expansion rate of the early universe to the expansion rate of the recent universe would be an exercise in futility if you assume a static constant. The very rules of expansion would be actively changing over billions of years.
It would perfectly explain the Hubble tension. The expansion mechanism itself would have fundamentally mutated between the era of the cosmic microwave background and today.
This highlights exactly why astrophysics is currently at a methodological impasse. To figure out which of these variables, if any, is the true culprit, we must rigorously scrutinize how we have historically measured the expansion of the local universe.
We need to analyze the mechanics of the tools that yielded that higher 73 kilometers per second per megaparsec measurement.
Since the early 20th century, practically all of our primary astrophysical tools have relied on electromagnetic methodologies. We use telescopes to capture photons.
The scientific reliance on electromagnetic observations is a deeply entrenched paradigm. Edwin Hubble himself established it roughly a century ago.
The entire methodology relies on capturing electromagnetic signals light across various wavelengths from distant objects, analyzing the spectral lines, and using the fundamental properties of that light to calculate both distance and recession velocity.
The anchor of this entire methodology is the mechanism known as the standard candle. Specifically, astrophysicists utilize type Ia supernovae.
A type Ia supernova is not just a standard luminous stellar explosion. It is an explosion with a highly predictable, standardized peak luminosity governed by strict quantum mechanical limits.
The physics governing a standard candle are tied directly to the Chandrasekhar limit.
Right. When a white dwarf star accretes matter from a companion star, it eventually reaches a critical mass threshold.
Approximately 1.4 times the mass of our sun.
At that exact tipping point, the electron degeneracy pressure fails to support the star against gravity. This triggers a runaway thermonuclear fusion of carbon and oxygen.
Because this detonation consistently happens at that exact mass limit, the resulting explosion has a known, absolute intrinsic luminosity.
By charting the light curve, the specific rate at which the supernova brightens and fades over time, astrophysicists know exactly how truly luminous the explosion was at its physical source.
From there, the geometric calculation is remarkably straightforward. Because you know the absolute luminosity, you can determine its exact distance from Earth by measuring its apparent magnitude.
How dim it appears in our telescopes. The inverse square law of light gives you a highly precise distance metric.
But distance is only half the equation for the Hubble constant. You know exactly how far away the host galaxy is, but you also need to know how fast it is moving away from us due to cosmic expansion.
To calculate that velocity, astrophysicists look at the redshift of the light.
As the object recedes, the actual wavelengths of the electromagnetic signals are stretched out, shifting toward the red end of the electromagnetic spectrum.
By measuring the exact degree of that spectral stretching, you calculate the recession velocity. You combine the supernova's exact distance metric with its recession velocity, and you yield an expansion rate.
It is a brilliant, elegant system that has served astronomy for decades. But we have reached the ceiling of its precision because of the inherent limitations of relying purely on electromagnetic signals.
Light is extremely fragile over cosmic distances. When we use standard candles, we are constantly at the mercy of the interstellar and intergalactic medium.
Light can be heavily obscured by cosmic dust. It can be scattered by intervening gas clouds.
The apparent luminosity can also be altered by the metallicity of the host galaxy, which fundamentally affects the opacity of the supernova ejecta itself. We spend an enormous amount of computational and observational effort simply trying to calibrate out these confounding variables.
We are trying to accurately estimate the extinction of light caused by 1 billion light-years of dust, which means we cannot completely eradicate the systemic uncertainties inherent to electromagnetic observation.
If you want to definitively solve a paradox as precise as the Hubble tension, independent, non-electromagnetic measurement modalities are mathematically necessary.
We need an entirely separate physical channel of information, one that isn't subject to dust, metallicity, or light scattering. This establishes the absolute necessity of utilizing gravitational waves.
Gravitational waves represent a complete departure from traditional astronomy. We are no longer observing photons. Gravitational waves are literal ripples propagating through the physical fabric of spacetime itself.
When massive objects accelerate, they alter the curvature of spacetime. That alteration moves outward at the speed of light.
To conceptualize this, it is directly analogous to the way a physical object displaces water and creates radiating wavefronts, but operating on a microscopic cosmic scale within the four-dimensional geometry of the universe.
The genesis of these spacetime ripples requires an environment of almost unimaginable gravitational violence.
You do not get detectable gravitational waves from a star simply burning or a planet orbiting. They originate from the catastrophic collisions of extremely dense, compact astronomical bodies.
Primarily the in-spiral and merger of binary black holes or neutron stars.
As these objects orbit each other at significant fractions of the speed of light, they shed orbital energy in the form of gravitational waves. They spiral closer and closer until they merge into a single entity, sending out a massive shock wave of space-time distortion.
Capturing that distortion requires arguably the most precise engineering in human history. This is the domain of the LVK collaboration.
LIGO in the United States, Virgo in Italy, and Kaigra in Japan. This is an international consortium of over 2,000 scientific members operating massive interferometers.
These are L-shaped vacuum tubes several kilometers long, utilizing ultra-stable lasers and mirrors isolated from the Earth's seismic noise.
When a gravitational wave passes through the Earth, it literally stretches space in one direction and compresses it in another. The LVK instruments measure that fractional change in the distance of their laser arms.
And the scale of this measurement is staggering. They're routinely measuring a change in distance smaller than 1,000th the diameter of a single proton.
Because the sensitivity of these detectors is so phenomenally high, astrophysicists were able to develop a gravitational wave counterpart to the standard candle.
It is known as the standard siren protocol. The traditional standard siren technique extracts physical distance purely from the gravitational wave itself.
It is a triumph of general relativity. By closely analyzing the specific morphology of the gravitational wave, signal the phase evolution, the frequency of the chirp as the black holes merge, and the amplitude of the signal, scientists can extract the intrinsic chirp mass of the binary system.
Because general relativity perfectly predicts how loud a gravitational wave should be based on that mass and orbital frequency, We know its absolute intrinsic amplitude.
We simply compare that intrinsic amplitude to the signal strength detected by the LVK interferometers on Earth, and we calculate the exact luminosity distance to the collision.
It is a completely pristine measurement. There's no cosmic dust blocking the wave. There's no metallicity interfering with the signal. The gravitational wave passes unhindered through all intervening matter.
But standard sirens have a critical bottleneck: the recession velocity problem.
You have this pristine, incredibly accurate distance measurement. But to measure the Hubble constant, you need the recession velocity. You need to know how fast that specific black hole merger is receding from Earth due to the expansion of space.
And determining that speed from gravitational waves alone remains exceedingly difficult. The problem lies in the physics of the black holes themselves. Black hole mergers, generally speaking, do not emit light.
Without an electromagnetic signal, there are no spectral lines to measure. If you have no spectral lines, you cannot measure the redshift, which means you cannot determine the recession velocity.
To calculate the Hubble constant using a standard siren, researchers typically require the simultaneous detection of an electromagnetic counterpart.
Light from the merger, such as when two neutron stars collide and emit a gamma-ray burst.
Alternatively, you would need a small enough localization volume in the sky to pinpoint the precise host galaxy the black holes lived in, and then measure the redshift of that specific galaxy.
But the reality of observational astrophysics is that finding that exact host galaxy among millions in a localized patch of sky is rarely feasible with binary black holes. The error boxes on the sky map are simply too large.
So we are left with a massive catalog of highly precise distances to black hole mergers, but no velocity data to pair them with. We are stuck.
That is, until a massive conceptual shift occurred, completely sidestepping this bottleneck. This paradigm shift was developed by researchers at the University of Illinois Urbana-Champaign and the University of Chicago, involving a team of prominent astrophysicists, including Nicholas Eunice, Daniel Holtz, Bryce Cousins, and their extensive network of doctoral and postdoctoral researchers.
What this team realized was that the field's focus on individual, perfectly resolved, standard sirens was blinding them to an even larger data set hidden in the noise.
They initiated a conceptual leap that shifted the analytical focus away from the rare, distinct black hole collisions that our detectors can individually isolate.
When you look at the LVK data, there is a strict bifurcation between observable events and unobservable events.
An observable event is a massive, relatively nearby binary black hole merger that produces a high signal-to-noise ratio, standing out clearly above the instrumental noise of the detectors.
But for every one of those loud observable events, there's a vast multitude of smaller or vastly more distant collisions happening constantly throughout the universe.
And those distant collisions register as too faint to be observed individually. Their signal-to-noise ratio is too low for the LVK pipeline to flag them as a distinct merger.
Instead, these unresolved signals blend together. They overlap in time and frequency. This brings us to the formal definition of the gravitational wave background.
The background is the cumulative overlapping signal, a stochastic hum generated by the countless unresolved black hole collisions occurring continuously throughout the cosmos since the era of peak star formation.
It is a pervasive background noise of space-time ripples.
So, if the LVK interferometers cannot resolve these individual distant mergers, how can this research team use them?
The key is statistical extrapolation. The researchers developed a methodology to mathematically harness this hum.
By carefully quantifying the precise rate and mass distribution of the observable individual black hole collisions that LVK can clearly detect, physicists can build a demographic profile of black hole populations.
From that localized demographic profile, they can statistically extrapolate the sheer volume of unobservable events occurring across the broader universe that are actively contributing to the background hum.
It requires immense computational modeling. You're essentially taking the localized population of binary black holes, integrating their expected merger rates over cosmic time, and projecting the total gravitational wave energy density they would produce.
This yields a highly predictable stochastic background spectrum, and this is where the new tool, the stochastic siren methodology, comes into play.
We must detail exactly how the stochastic siren methodology functions. It is named for the random, distributed nature of the countless black hole mergers that collectively generate this background signal.
The entire method hinges on a rigorous geometric correlation between the Hubble constant and the physical volume of the gravitational wave background.
The researchers discovered a profound inverse relationship, broken down into a precise, step-by-step logical sequence.
Let us trace the geometry of this correlation. Step A requires us to postulate a scenario where the Hubble constant is smaller.
Essentially adopting the lower value derived from the cosmic microwave background data. A smaller Hubble constant definitively indicates a slower rate of universe expansion.
Moving to step B, we logically deduce the geometric consequences of that slower expansion rate. If the universe has been expanding more slowly to reach its current observable state, the total volume of the observable universe at any given redshift must mathematically be smaller than it would be in a faster expanding model.
The cosmological container stretching back into the past is physically more compact.
Which brings us to the critical inflection point, step C. We must conclude that if the universe's geometric volume is smaller at those distant redshifts, but the intrinsic statistical number of black hole mergers occurring in the universe remains constant based on star formation rates, then a profound spatial compression occurs.
The same vast number of black hole mergers must be compressed into a much tighter region of co-moving space. The spatial density of these catastrophic events spikes significantly.
And that density leads directly to step D. We mathematically determine that this increased spatial density of black hole collisions would unequivocally amplify the overall strength and volume of the gravitational wave background.
Because the sources are packed closer together in a geometrically smaller universe, the cumulative space-time ripples they produce would compound. The resulting stochastic hum would be significantly louder and stronger.
This sequence establishes the inverse relationship that serves as the foundation of the entire diagnostic tool. A smaller Hubble constant strictly mandates a louder gravitational wave background.
And this inverse relationship functions as an extraordinarily potent analytical tool through the process of elimination.
The methodology relies on constraining the parameter space of the Hubble tension. If terrestrial instruments, specifically the highly sensitive LVK interferometers, fail to detect this amplified, highly potent background signal through cross-correlation analysis, then astrophysicists can mathematically rule out the slower universal expansion rates.
The non-detection becomes the empirical data. If the lower bounds of the Hubble tension, those derived from the early universe measurements, were correct, the stochastic hum would be theoretically deafening to the LVK sensors.
It would dominate the low-frequency sensitivity bands of the detectors. This is the empirical application of the methodology, which the research team has already begun applying to existing LVK data runs.
Even without a definitive, isolated detection of the background hum, the analytical power of this method is already yielding highly significant results.
By analyzing the data from the LVK's recent observing runs, the team utilized the absence of a massive stochastic signal to establish firm upper limits. They quantified the maximum possible volume the background hum could be producing without triggering a detection in the current data.
By establishing these strict upper limits, proving definitively how loud the background is not, they have effectively ruled out the slowest expansion models and the most extreme variants of the early dark energy hypothesis.
They have placed a rigid mathematical ceiling on the cosmological models.
And the researchers did not stop at simply ruling out models. They moved to refine the Hubble constant itself.
The methodology synthesizes two independent streams of gravitational wave data. By combining the upper limits of the unresolved background hum with the pristine distance data extracted from the isolated individual standard sirens, the massive black hole mergers, the team achieved a highly refined, independent estimate of the Hubble constant.
The significance of that synthesis is that the new estimate falls directly within the parameter space of the Hubble tension.
It does not blindly validate one side over the other. Rather, it provides a highly constrained, completely independent physical measurement utilizing a fundamentally distinct physical force.
As the interferometers improve, this measurement will only become more precise. The technological projections over the coming decade indicate a rapid convergence.
The LVK network is continuously undergoing significant sensitivity upgrades, reducing quantum noise and improving seismic isolation. There is a broad scientific consensus that within approximately 6 years, during the upcoming observational runs, detector sensitivities will have increased sufficiently to cross the critical threshold.
Within 6 years, they project we will definitively detect and precisely constrain the exact volume and spectral shape of the gravitational wave background.
We will definitively isolate the hum from the instrumental noise.
The ultimate objective of this timeline cannot be overstated in its importance to physics. Securing this independent, precise measurement via the aggregate space-time ripples of millions of black holes is fundamentally necessary to definitively resolve the Hubble tension.
It completely bypasses the limitations of electromagnetic standard candles, the cosmic dust, the metallicity, the extinction rates, and it bypasses the recession velocity bottleneck of individual standard sirens.
It is a purely gravitational mechanism to correct our baseline understanding of cosmic age, universal geometry, and the dark components of our universe.
To synthesize this methodology academically, the stochastic siren method possesses the profound capacity to leverage the macroscopic, unresolved dynamics of the cosmos. It relies on the statistical aggregation of unobservable events to calibrate the geometric expansion of the universe.
It reasserts a critical paradigm in astrophysics. The utilization of unresolved cosmic data, the background, hums itself to solve foundational physical paradoxes that localized, isolated measurements simply cannot reconcile.
It is a masterful application of statistical mechanics and general relativity applied to cosmology.
As we conclude this exhaustive examination of the stochastic siren methodology, there is a rigorous, highly provocative extrapolation for you to consider independently. When the LVK network or future generations of detectors like Cosmic Explorer eventually map this gravitational wave background, they will not merely be recording its overall amplitude.
They will eventually map its specific directional anisotropies.
Just as the cosmic microwave background has a microscopic temperature fluctuations across different regions of the sky, the gravitational wave background will possess anisotropies, a subtle unevenness in the hum originating from different cosmological coordinates.
Consider the implications of that topography. The precise spatial distribution of these spacetime ripples could map the density of matter before the cosmic dark ages.
Furthermore, variations in this background might reveal entirely new, pre-Big Bang structures predicted by cyclic cosmology models, or even expose the gravitational signatures of previously theorized higher dimensions of spacetime leaking into our observable universe. Phenomena that our current lambda CDM expansion models cannot even formulate.